Morning.
Professor Musgrave,
Yeah.
in the syllabus, didn't it say that if you get like above a 90 on all 4 tests, you can exempt the final?
All four complete test grades, yeah.
Yeah.
Yes. That's what it says. All right, folks, it's 8 o'clock. We'll get started. Please enable your video if you haven't already done so. Max, cheers. Thank you.
I'm on my phone and my front camera is broken, so I can't really use it.
Okay. All right, Max. Thanks for letting me know. All right, so we're going to start here on concentration and colligative properties. This is, or if you've been in my Chem 1 class, then you would have seen this before, but if not, then you may not have. Okay, so we're going to start off with concentration, and concentration in general is going to be well, certainly an amount of solute over an amount of solvent or possibly solution. So let's look at some definitions here. So a solute is something that's going to be dissolved. So the concentration is always going to have an amount of solute on top. Down here we have a solvent. When the solute goes into a solvent, we get what's called a solution. So it's important to see the distinction between the word solvent and the word solution, and the fact that the solution is really the solute plus the solvent together. Does anybody have any questions so far? Okay, so that's our working definition of concentration. So what I'm going to show you here are 4 methods by which we can calculate concentration. They're all a little bit different. The first one we're going to be looking at is called percent weight. And in this instance, we take the mass of a solute and divide it by the mass, or effectively of the solution, which is the mass of solute plus the mass of solvent. Multiply by 100%, that'll give us the percent weight. Molarity is going to be moles of solute divided by liters of solution, which again is going to be liters of the entire thing. You'll see that this one's going to be determined, it's going to matter whether the solute is a solid or a liquid. Molality is one you might not have heard of before, is moles of solute over kilograms of solvent. And mole fraction is going to be moles of solute divided by moles of solute plus solvent. This is not a percentage, it's just a fraction. All right, so let's go ahead and look at some examples of these. Now we're going to first of all discuss solid solutes. Now the distinction between a solid solute and a liquid solute is that a solid solute won't tend to change the volume of the solution very much. So you can take an Alka-Seltzer, for example, stick it into water, it's not really going to change the volume very much. However, if you were to add a liquid to water, like, I don't know, Pepto-Bismol or something like that, you know that that would change the volume and that would have an effect on the volume of the solution. So it's important to be aware of the distinction that I'm making here. So here's an example. For a mixture of 22 grams of phenol, and I'm pointing out this is a solid, I also give it an abbreviation P for it, as for phenol. And I also provide the molecular formula as well, C6H6O. You'll see where that comes into play later. And 160 grams of acetic acid, C2H4O2. Calculate the following concentrations. The density, I give the density of acetic acid as being 0.800 grams per mil. So to look at the formula for percent by weight, it's always the mass of solute divided by the mass of solute plus the mass of solvent. So let me tell you some tips here for determining what the solute is and what the solvent is. One easy way is to look at the amounts. Generally speaking, the solute is always less than the solvent. That's one thing. The other thing is that the solvent can never be a solid. That's an obvious one there as well. And you know, those are the main clues that I can tell you for determining what the solute and what the solvent is. The other thing is by looking at the actual question, and it says percent weight of phenol. And whenever we're asked a question about concentration, it's always with respect to our friend, the solute. So if I'm being asked about phenol, I know automatically that's the solute as well. So there's lots of different things that we can talk about with that. Let's see, how are you doing so far with it? And you can ignore the last one again. So, how are you doing so far? 5, 4, 3, 2, 1. All right. Any questions? Okay. So for this one, it's 22 grams of phenol over 22 grams plus 160 grams. You can see that we've got 160 grams of the acetic acid, 22 grams of phenol. So that's not particularly difficult math to do there. It comes out to be 12%. That's two significant figures because of the 22 on the top. We add these together, that would actually be three significant figures because addition goes by number of places past the decimal. So that would end up being 2 sig figs over 3 sig figs, which gives 2 sig figs. Now, molarity. Now, this one really does depend on whether you've got a solid solute or a liquid solute. So you can see that with a solid solute, now I'm going to actually give you another example here. I'll make this a solid. And I'll say that the volume V does not change significantly. But I'll just say it doesn't change. But let's say we've got a liquid. This would be a liquid solute. And this is the solvent still. So this would be the solution. You'll notice that the volume of the solution is equal to the volume of the solvent plus the volume of the solute. And I think that's a really important distinction that we need to be aware of here. So that's the difference between a solid solute and a liquid solute. And the one concentration unit it affects is going to be molarity, because molarity is based on the moles of solute over liters specifically of solution. So if it changes for liquid but not for solid, then that means we're going to have to handle molarity differently depending upon whether we're dealing with a solid or a liquid. Now, I'm going to stop here for a second because this is a really important point and I want to see if people actually understand that. So how do you feel about my distinction here that I'm making about volume of solution depending upon a solid solute and a liquid solute? 5, 4, 3, 2, 1. No, somebody doesn't want to vote. No, somebody is voting. Okay. Okay, so questions. Questions. Because there's one person who doesn't understand or halfway understands. All right. So looking at how we handle molarity, then we need to find moles of solute. So the first thing we need to do is find the moles of the phenol, because that's the solute here. It's going to be 22 grams times 1 mole over 94.00. So where am I getting the 94.00 from? Well, I am given the molecular formula of the phenol here in the problem, C6H6O. So all I need to do is go onto the periodic table and add up all the atoms, of course, to find the molecular weight. So 6 carbon, 6 times 12 is about 72, plus 6 is 78, plus 16 is about 94. So that's how I'm getting the 94 grams there for the molar mass. So 1 mole is 94.00 grams, remembering that that's what the dimensional analysis is telling us. So that tells us that we're getting 0.23 moles of solute. The other thing we need is the volume of the acetic acid, because that is the only thing that's going to matter. We don't have a volume for the phenol because it is a solid, but we do need the volume of the acetic acid. In order to get that, we need to apply the density. And we are given the density as part of the problem. So let's look at how density comes into play and how that is going to affect our calculations. So I'll put it in down here. So density is mass divided by volume. If I want mass, it's going to be density times volume. And if I want volume, it's going to be mass divided by density. So what we have here is, in this problem, we have a mass of acetic acid. We also have the density. So you can see that it's going to be mass divided by density. So how do we express that? Well, the density, as I said, was given as 0.800 grams per mil. To make this work, another way of expressing this is going to be mass times 1 over density. So the density here is 0.800 grams per mil. If I flip it, and that's what 1 over density would mean, then it's 1 mil over 0.800 grams. That allows the grams to cancel. And the other thing that needs to be done here, it needs to be liters of solution. So I multiply by 1 liter over 1,000 mils, and that gets me to my volume of solvent, which is 0.200 liters. After that, we get the molarity by dividing the two, the moles and the liters, and that gives us our molarity, which is in big M. Big M is also expressed as moles per liter. All right, does anybody have any questions? Anybody have any questions? All right, how do you feel about molarity? That's the hardest one, I think. How do you feel about molarity? How do you feel about molarity? Okay. Okay, any questions? We've only got 8 people here, so it's hard to.
Can you show how you got the volume of acetic acid again?
Okay, so it's going to be, if you look at the formula, are you okay with the density formula here that I have, mass over volume?
Yeah.
And how about the rearrangement of it? So volume is mass divided by density or times 1 over density. Is that okay?
Yeah.
Okay. So the density is given in the problem as 0.800 grams per mil. 1 over density would be 1 mil divided by 0.800 grams. And that's what I'm doing here, mass times 1 over density. So 160 dot grams times 1 mil over 0.800 grams. That makes the grams cancel. The other thing we need to do is convert into liters. That's why I multiply by 1 liter over 1,000 mils. Does that make it a little clearer?
Yeah.
Are you sure?
Yeah, I get it now.
Okay. Does anybody have any other questions about this, about molarity?
I have a quick question, not about molarity.
Okay, what's your question, Alexandra?
So about the whole like solid solutes and liquid solutes, the way that we would figure out if it's a liquid solute is if we added up the solvent and solute and if it equaled the solution volume.
Well, the thing is, you'd have to, you wouldn't have to, you wouldn't have the solution volume to begin with. You'd have to know that the solute you were dealing with was a liquid or a solid. So either you'd have to be able to tell, and you could tell if you were given mils, for example. The other way you know is if you were given a density. So if you weren't given a density and it was in grams, then you would have to assume it was a solid. But I think in all the questions I give you, I actually tell you if it's a solid.
Okay.
Is that fair enough, Alexandra?
Yeah.
Okay.
Yeah. Thank you.
In other words, no, you're not left with any doubt as to what kind of solute you're going to be dealing with. Certainly not any of the problems I give you. Okay.
So what was the difference in the problems? Because you said that there was a difference if it was a solid or a liquid.
Okay, so in the case if it's a liquid, the volume of the solution, you'd have to add them together. You'd have to add up the volume of the solvent plus the volume of the solute. You'll notice here, because the phenol is a solid, all I'm considering here is the volume of the solvent, which is the acetic acid. But you'll see,
Okay.
you'll see in a second when I handle liquid solutes that the step we do there, actually, spoiler alert, I'll show you here. You see how we have to add these together to get the volume of the solution.
And that's a liquid solute.
Yeah,
that
that example, yeah.
Okay.
That's going to be the difference, Alexandra. That's the most common error students make, is they forget to take into account the liquid. It's just remember, I always just tell people to think about Alka-Seltzer in water, how it doesn't really change the volume. But then if you take a liquid and add it to water, it does change the volume of the solution.
Okay. So the question that we're doing right now is a solid solute.
It is. It is. And we know this because you see, look at this.
Oh, because it literally says solid.
Yeah. Also,
Okay.
well, the fact it's in grams is not really that telling, but the fact that it does say solid, and the example is about solid solutes, you know, that's how we know.
Okay, thank you so much. I get it.
Okay, but just realize that I do tell you in the questions as well. I don't leave it as some sort of mystery, okay?
Okay. Thank you.
Oh, you're welcome. Now, molality is a little bit different. Now, the difference between molarity and molality, if you look at the two formulas, I know they sound kind of similar, but the molarity is moles of solute per liter of solution, and that's a volume, whereas the molality is moles of solute over kilograms of solvent, so it's a mass of solvent, and specifically it's a mass of solvent, not a mass of solution. That's really important to note as well. The reason that molality is sometimes used over molarity is that a mass of something doesn't change when the temperature changes. However, a volume of something can change when the temperature changes. So what we know is that liquids will expand when they're heated and they'll contract when they are cooled. So what that means is that the solution molarity can be dependent on the temperature. I'll say that again. The molarity can be dependent on the temperature. However, molality doesn't change with temperature. So for applications where temperature changes are occurring, molality is what we tend to use. And we'll see that when we do some colligative property calculations. But that's the essence of what's going on here, of a difference between molarity and molality. Does anybody have any questions about this so far? Okay, so it's always kilograms of solvent. Now, unlike the molarity, there's no difference here if the solute is liquid or solid, all right? So it doesn't matter because the change in the volume of the solution is immaterial here. All that really matters is the kilograms of solvent that you originally had, and that's never going to change regardless of whether it's a solid or liquid solute that you're using. So I think that's important as well. We already got the moles of phenol previously in part B. I got it by multiplying by 1 mole over the molecular weight. That's where the 0.23 moles is coming into play. The other thing we need is the kilograms of solvent. And to do that, we have the mass, which was given in the problem, 160 grams of acetic acid. And we multiply by 1 kilogram over 1,000 grams, which gives us 0.160 kilograms, which is going to be the mass of the solvent in kilograms. We take the two, we divide them, and we end up getting 1.4. And the unit we use for molality is little m, which is also equivalent to moles per kilogram. So summarizing so far those units at the end, big M is equivalent to moles per liter. Little m is equivalent to moles per kilogram. Does anybody have any questions so far? Any questions so far? Okay. Mole fraction. Here I've asked for the mole fraction of both substances. I'm doing this for a specific reason. You'll see why in a minute. To get the mole fraction of something, what we do is we do moles of the solute, in this case P, mole fraction of P is going to be moles of P divided by moles of P plus moles of A, or moles of AA, which is acetic acid. We already had the moles of a phenol from before. We got it from part B, 22 grams times 1 mole over the molecular weight. What we don't have is the moles of acetic acid, but we do have the mass of it, and we do have the molecular formula. So the molecular formula here, C2H4O2, that's 24 plus 4 is 28, plus 32 is about 60. So the molecular weight is 60 grams per mole for that one. So 160 times 1 mole over 60.00 grams. That gives me the moles of acetic acid, which is 2.67 moles. When we do the math on this, we get 0.23 moles over 0.23 plus 2.67. And that gives us two significant figures, 0.079, remembering that leading zeros are never significant. Any questions so far about mole fraction? The symbol here is called chi. It's a Greek letter, and that's usually used to denote mole fraction. It looks like an X or a stylized X. All right, let me see how you feel about mole fraction. How do you feel about mole fraction? How do you feel about mole fraction? 5, 4, 3, 2, 1, 0. So any questions about mole fraction so far? To get the mole fraction of acetic acid, we use moles of acetic acid over again the moles of phenol plus the moles of acetic acid. And you can see we come out with 0.921 there as a result. If you look at these two, you'll notice something, and that is if you add these together, it comes out to 1, which is kind of what we expect. If we've got two fractions of something, then adding those fractions together should give the whole, and the whole would be 1. So another way that we can get the mole fraction of acetic acid, if we know the mole fraction of phenol, would be to take 1 and subtract 0.079, which would also come up with the exact same result, even with significant figures. Does anybody have any questions about getting the mole fraction of acetic acid? Okay. So this example here is a little different because now we're using a liquid solute. And here I've given the liquid, and you can see here that I have actually told you it's liquid as well. Although the fact that it's in milliliters is also a bit of a giveaway. And also the fact I've given you a density is a bit of a giveaway too. So there's a lot of information here that tells you that we are dealing with a liquid solute. The other thing is, if we look at what we're actually dealing with as far as solute and solvent, you can see the furfural, which is what I'm calling F, is going to be the solute because there's much less of that than there is the ethanol, which is the solvent. And of course, the other clues here, if you look throughout the questions, we're looking for the percent weight of furfural, which again is a big giveaway, but that is the solute. Does anybody have any questions so far? So the percent of solute here is the mass of solute over the mass of solute plus the mass of solvent as it was before, but we don't have a mass of solute. All we have is a volume. In order to obtain the mass of the solute, we have to take the volume and multiply it by the density. So that's a little different to what I did earlier, because earlier I was looking for a volume. I was looking for a volume of a certain substance. It was the solvent, I think, last time. But here I'm looking for a mass, and I've been given the volume. To get the mass, it's density times volume. And you can see that when you look at the units, the mils will cancel, you're left with grams. So that's how you know what you're getting here. Does anybody have any questions about how I'm getting that mass of furfural? Any questions? So to get the percentage of furfural then, we are given the mass of this solvent here. So it'd be 25 grams over 25 grams plus 160, which comes out to 14%. All right. How do you feel about percent weight in this example? How do you feel about it? How do you feel about percent weight? 5, 4, 3, 2, 1. Okay. All right, any questions? Okay, it's a molarity of furfural. This is the one that's different from the one we looked at with the solid solute. In this case, because it's liters of solution, and I've made a big deal of this here, you can see that in the case of the solid solute, the volume does not change significantly when we add the solid solute. However, if we add a liquid solute, you'll notice that we do get a noticeable change in the volume of solution. So the difference here between the solid solute and the liquid solute, solid solute and liquid solute, is that to find the volume of the solution, we have to add the two things together. So we have to find both the volume of the solvent, and I think we were already given the volume of the solute in the problem, which was 22 mils. You can see it up here. But we have a mass of solvent here that needs to be converted into a volume. And to do that, we do what we did earlier. to find a volume, it's mass times 1 over density, which is what I've done here. So to get the moles of furfural, it's going to be 25 grams times 1 mole over the molecular weight, remembering that you are given the molecular formula here in the problem. I think in the test problems I actually give you the molecular weights automatically, so you actually don't even have to calculate those. They're given to you in the problem. I'll show you that in a bit. Sort of makes it a little bit easier. And then, you still find the moles by the same route. You do it by taking the mass and multiplying by 1 mole over the molecular weight. The volume of ethanol we need to find because we need the volume of both the solvent and the solute. We already have the volume of the solute. It was given to us in the problem. But for here, I needed to find the volume of the ethanol, which is the solvent. And that comes out to be 203 mils when we do 160 grams times 1 mil over 0.789 grams, which I get from the problem again as the density. There it is there, 0.789 grams per mil. We flip it over, that's 1 mil per 0.789 grams. We add the two volumes together, which comes out to be, in this case, 225 mils. We convert that to liters because it's liters of solution. And then we divide the two and we get our molarity that way. Okay, so how do you feel about molarity involving a liquid solute? Molarity involving a liquid solute, how do you feel about it? 5, 4, 3, 2, 1. Okay.
I just have a quick question.
Yes, Alexandra, yeah.
So I know you're gonna go through like the ungraded tests at like near the end of class, but for the exam, is this gonna be like a one ginormous question kind of thing?
No.
Okay, good.
No, it's all split up and they're all different problems. Sometimes you'll be asked for molarity, sometimes for molality. Sometimes,
okay, that makes sense.
Yeah, I mean, but I suppose you could be expected to be asked one of each, right?
Mm-hmm.
Now, just a caveat here as well. There's problems we're going to do in a minute that are colligative property problems where you may have to calculate a concentration and then use that concentration to solve the rest of the problem. So I'm just warning you about that as well. But again, those are all separate problems. It's not one massive problem. Okay.
Okay, cool. Thank you.
Okay, you're welcome. Any other questions? Okay, so molality in this case is moles of solute over kilograms of solvent. Again, just solvent. And you'll see I make a big deal of getting the mass of the solvent here. And the mass of the solvent is going to be 160 grams times 1 kilogram over 1,000 grams because we need it to be in kilograms. But you'll notice the distinction here between these two problems. In the case of the molarity, I needed liters of solution, which necessitated that I add the volume of the solute to the volume of the solvent. In the case of molality, we're only ever interested in the solvent. So there's no need to even consider the solute here. And this is exactly the same as what we did when we had the solid solute. You'll notice all we did was just take the kilograms of solvent. Again, just the same deal. So that's what we're doing here is we're taking the mass, which was given in the problem, by the way, is 160 grams, converting it into kilograms. We already had the moles from part B up here, and we divide that by the kilograms of solvent that we calculate here. So that gives us 1.6. And remember, it's little m, and little m is the same as moles over kilograms. Big M is the same as moles over liters. Okay, how do you feel? Let's see how you feel about molality. How do you feel about molality in this case? How do you feel about it? 5, 4, 3, 2, 1. Getting one person who's not voting at all. Okay. Mole fraction, the same deal as what we had before. So we need to find the moles of furfural, which we already had. It was 0.25 moles. We got that from part B. We do need the moles of the ethanol as well. And we get that by taking the mass and dividing by the molecular weight, because we do have the molecular formula. This is back in the problem over here. And we have the mass and we have the molecular formula. So we can find out the moles of the ethanol as well. And that allows us to get the mole fraction, which would be the moles of the solute divided by the moles of the solute plus the moles of the solvent in this case. So because we're looking for the mole fraction of the solute. We can also do the mole fraction of the solvent as well. And you can see that just reverses it. And again, you notice how these add together to give 1, which would be what we'd expect for a mole fraction. Does anybody have any questions about mole fraction here? Okay, so that doesn't change either. The only thing that changes when we're going from a liquid solute to a solid solute is the molarity, because the molarity depends upon liters of solution. So it's what I was talking about earlier, how you add the solid solute in, it doesn't change the volume of the solution much. Whereas if you add a liquid solute in, you can see that it does change the volume of the solution. So that's why the distinction and why we have different methods for solving the two. But it's only the molarity that matters here for that. All right, does anybody have any other questions? Okay. So we're going to talk about colligative properties now, and we're going to apply what we learned about concentrations to the colligative properties. Now, colligative properties are such that they are affected not by the nature of what's being dissolved, but simply by how many particles are dissolved. So examples of colligative properties are freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. So what I'm going to do at this point is I'm going to go through and show you how these colligative properties occur, or at least give you some sort of base explanation as to why that happens. The first one we're talking about here is called freezing point depression. So if you put something, a solid, for example, on top of ice, and that solid is soluble in water, what will happen is that the ice will melt in order to dissolve the X that you've put on top of it. So what this effectively does is it lowers the freezing point. So this is the reason up north that they put salt on the roads. Salt is soluble in water. So what happens is you put it on top of the ice melts, turns into water, and also has the effect of lowering the temperature at which the ice actually becomes solid water. And that can mean, I mean, if you have the right ratios of solid to ice, you can actually lower the freezing point by a good amount, by maybe 10, even 20 possible degrees Celsius, which is a lot, which allows for the temperature to cool down and not have ice form on the road. So that's the whole intent of putting salt on top of the ice. So it does actually lower the freezing point of the ice. Does anybody have any questions about freezing point depression so far? Okay. The next two we're talking about are going to be boiling point elevation and the vapor pressure lowering. So generally speaking, if you've got a pure liquid that hasn't got anything dissolved in it, you'll have liquid, but above it, you'll also have molecules of vapor floating around as well. And that vapor actually has a pressure that can be measured. If you dissolve something into a liquid, what will happen though is that some of that vapor will come back down into the liquid to help dissolve whatever it is you've put in the liquid. this has two effects. The first effect is that it lowers the vapor pressure because now you have less vapor above the liquid than you did before. That's the first thing. The second thing is that now it requires more energy, and that is greater heat, to take that liquid and turn it into a gas, because now the X's that were making up the vapor, they're now associated more with the liquid because they're helping dissolve whatever you've put in the liquid. So what this has the effect of is raising the boiling point. It now takes more energy to turn that liquid into vapor. So this means that we're going to have a higher boiling point. Now this is actually applied in cooking. So a lot of people, when they cook pasta, they add salt. They add salt into their pot. Now this does have the effect of making it saltier, which makes it more tasty, but the other thing it does is it raises the boiling point of the water as well, because now the water has a harder time becoming vapor because it's trying to dissolve the salt that's been added into the liquid. So this has the effect of raising the boiling point and also cooks the pasta a little bit faster, because now you can cook it at 110 degrees Celsius rather than 100 degrees Celsius. So that's the effect of adding the salt. Does anybody have any questions about boiling point elevation or vapor pressure lowering? Okay. The last one is called osmotic pressure. And osmotic pressure, what you're doing is you have this U-shaped tube. On one side, you've got pure solvent, and on the other side, you've got a solution. So it's a solvent with some solute in it. And in the middle here, separating the two, we have a semi-permeable membrane. Now, semi-permeable membrane is called such because what it does is it allows for passage of the solvent to go into the solution, but not the other way around. So the molecules of the solute can't get to the other side of the semi-permeable membrane. Now, what happens here is that with the pure liquid or the pure solvent coming through the semi-permeable membrane to help dissolve whatever's on the other side, it produces a osmotic pressure. So if this is a piston, then this is going to be forced upwards, which creates a pressure. That pressure is denoted by the capital pi, capital Greek letter pi. That's a big pi there. Now, the semi-permeable membrane, as I said, is something that allows for the passage of solvent, but not solute. So I'll give you an example of osmotic pressure, and it might be something that you've done in a biology class. A lot of the time, they do an experiment where you take a potato and you stick it into salt water. Now, the skin of the potato is actually acting as a semi-permeable membrane. So what will happen is that there's stuff inside the potato that there's going to be pure water in there, and the pure water can leave the potato and go into the saltwater solution. This has the effect of shrinking or shriveling the potato. So that's an example of osmotic pressure right there. Does anybody have any questions about osmotic pressure? Okay. How do you feel so far about colligative properties we talked about? Anybody have any questions? No. Looks like everybody's okay with that. Okay. All right, so let's look at some examples and how we can apply what we've talked about previously to colligative property calculations. Okay, so we've got the freezing point. Now here I'm using the concentrations that I calculated first at the beginning of the class here to do this, to do these specific examples. Now this is actually a lab you did way back at the very beginning of the course here, and we actually worked out the molal freezing constant of water, if you'll recall. And sorry, what do we do? Maybe it was a molal freezing constant, yeah. So we were looking at Kf. And to do that, we dissolved salt in ice water and figured out what the temperature was and the effect it had on lowering the freezing point. So let's say you've got a freezing point, you're looking for the freezing point of the above solution. Now the solution I'm talking about is this one. It's a phenol in acetic acid, so that's what we're looking at. Now what we are given here is the freezing point of pure acetic acid, which is 16.6 degrees Celsius. And we're also given the Kf, which is 3.90 degrees Celsius per molal. So that's the molality that we're using there. So in order to calculate delta TF, I'll actually do these. We're using this formula. Again, this is a formula you'll be given. You do not have to memorize this. But delta TF is given is Kf times molality, which is little m here. Now the Kf you can see is 3.90 degrees Celsius, and that's little m to the -1. And that's multiplied by the molality, which is 1.4 little m, which comes out to be 5.5 degrees Celsius. And what this represents is the actual freezing point depression. So let me go back and show you where I'm getting the 1.4 from. So when we did the problems initially, we had to calculate the molality of phenol, which I did, moles of solute over kilograms of solvent. I came out with 1.4 little m. So that's how I'm getting the molality there. The Kf was given in the problem. You can see it here. And we multiply those two together. That gives us the 5.5 degrees Celsius, which is the freezing point depression. Now, the question you might have is, how do I know it's freezing point depression and not freezing point elevation? Well, it's going to be freezing point depression and boiling point elevation. But one way I kind of remember that is sometimes people get depressed when it's cold. So you can sort of think of it that way. So in order to calculate the new freezing point, what I have to do is take 16.6 degrees, which is the pure one that I'm given here, and I subtract. It's very important I subtract here to get 11.1 degrees Celsius. So for freezing point depression, you're always going to subtract the change in temperature that you calculate based on the formula that you're given for the freezing point depression. Does anybody have any questions so far? How do you feel about freezing point depression? 5, 4, 3, 2, 1. All right, that's good. Everybody seems to be on board with that. Boiling point elevation is very similar. Now, if you look at the way that that's set up, it's now going to be Kb, which is the molal boiling constant. That's you given here. That's here in the problem. Again, same units, degrees Celsius per molal. We're also given the boiling point of the pure solvent as well as being 118.0 degrees Celsius. So we take the Kb multiplied again by the same molality, right? So it's the molality that we calculated earlier, just like I did previously. We multiply those together. That gives us the change in the boiling point. That's delta Tb. Now, instead of subtracting, in this case, we add. And we add it because it's boiling point elevation. That's the key word there, elevation. The boiling point goes up. So that becomes 122.3 degrees Celsius. So the difference between these two, they both use molality. And in both instances, you're still trying to find a change in the temperature, the delta TF, which is going to be K times M, KF or KB times M. In the case of freezing point, you subtract. In the case of boiling point, you add. Freezing point depression, boiling point elevation. Does anybody
have a
have
question?
Yes, Alexander.
Are you using the molality of the solute or the solvent?
Just the solute, because
Okay.
in the case of colligative properties, what we're looking at is we're always focusing more on the solvent, but in order to do that, we need to figure out how much solute is dissolved, because colligative properties are all about how much solute is in the actual solution.
Okay.
I hope that makes sense. It's
Yeah, it does.
it's an interesting distinction though. With concentration, we're only ever interested in the solute. But then when we're talking about colligative properties, we're more interested in the properties of the solvent. In this case, we're looking at the boiling point or the freezing point of the actual solvent after you've added the solute to it. So it's a kind of a subtle point, but that's important. All right, does anybody have any other questions? Okay. Vapor pressure. There's a formula for the change in vapor pressure that results from adding a solute into a solvent. And the formula is as follows. Again, not one you have to memorize. Delta P solvent is equal to mole fraction of solute times P naught of solvent, where P naught of the solvent is the vapor pressure of the pure solvent. So I have the question up here, vapor pressure of the bulk solution, and I give a temperature. The reason the temperature has any relevance here is that vapor pressure changes depending on the temperature. So as you can imagine, if the temperature is lower, the vapor pressure would be lower. If the temperature is higher, the vapor pressure is higher. As it turns out though, the fact that the temperature is 25 degrees Celsius doesn't really play into the problem at all. All it allows us to do is to tell us that we have a vapor pressure of the solvent at that specific temperature. So it's 20.0 torr at 25 degrees Celsius. But the only thing that really matters is that it's 20.0 torr. So what's a torr? A torr is a millimeter of mercury. Now I'm expecting at some point you've seen this before. Well, actually I know you have, because we did it back in test 2 when we were talking about units of pressure. And we also talked about vapor pressures back then as well, if you remember. So 1 torr is 1 millimeter of mercury. Not that that really matters that much here. The mole fraction of the solute, let's go back to where I calculated the mole fraction. It was back here where I got the mole fraction of the phenol. And I did that by doing the moles of phenol over the moles of phenol plus the moles of acetic acid. And the result I came up with for the mole fraction of the actual solute was 0.079. All right, so that's where that 0.079 came from. We multiply that by the pressure of the solvent, the pure solvent, the vapor pressure, and it comes out to be 1.6 torr. So what this represents is the change in the vapor pressure of the solvent. In order to get the new vapor pressure, it's vapor pressure lowering, and I gave you some context for that before. You'll notice that when we dissolve stuff in liquid, vapor molecules come back down into the liquid and help dissolve whatever's in there, so it lowers the vapor pressure. So we take the pure vapor pressure and subtract what we came up with here, the 1.6 torr. That comes out to be 18.4 torr. Does anybody have any questions about vapor pressure? Okay. The last one is osmotic pressure, and the formula for that is big pi is equal to mRT, where m is the molarity. The R value is a constant, 0.08206 liters atmospheres per mole per Kelvin. And you can see that the temperature here, which was 25 degrees Celsius, has been converted into Kelvin. If you look at the formula itself, the pi equals MRT, it might look a little familiar to you. So you remember that there's another formula that we're familiar with for gases, and it's called PV equals nRT. I can rearrange this a little bit, and I can do P equals N over V times RT. Now, N over V is moles over volume, which is actually kind of equivalent to molarity. So even though this is a gas equation, this is a modified equation for osmotic pressure, which kind of ends up being a similar kind of situation. Now, the 1.2 moles per liter for the molarity, I got that when I calculated it earlier. Back up here, molarity of phenol, 1.2 moles per liter, which gives our final pressure of 29 atmospheres. So it's a pretty big value. Osmotic pressures are pretty big. And yeah, there are situations where we can apply that to a situation called reverse osmosis. And reverse osmosis can be used to actually purify liquids. Now, the trick here is this. We know that the pure solvent here going across the semi-permeable membrane is actually going to create a pressure on this piston here. However, if we can create a pressure on this piston that's greater than the osmotic pressure, what we can do is we can reverse the situation and push down on this and push the pure solvent back past the semi-permeable membrane, but leave the solute in the solution on this side of the semi-permeable membrane. So that way we can increase the volume of pure solvent on this side, and then that can be used as pure for pure applications. So that's how reverse osmosis works. It's a little bit tricky because it requires all sorts of filters and things, and those filters get gummed up. So it's not an incredibly efficient method, or it's a very high, cost a lot of energy in order to do that because the osmotic pressure is so high in order to make that happen. Does anybody have any questions? All right, so that was it for that. Let's go take a look at the test here. And you can see the kinds of problems that you'll need to be able to look at. Okay, so concentrations. So for this one, you're asking for the mass percent of X, then the molarity of X, the molality of X, and the mole fraction. So 4 different questions, one of each. And it's I said that you'd know whether it was a liquid or a solid. And so what I'm telling you here is that for the solids, I actually say it's solid. For the liquids, you'll be given either a volume, which is going to be obvious there, and a density, and that will help you to be able to calculate a mass if you need to. So notice that that's in all of those kinds of cases. But if it happens to be a solid, you'll be told it's a solid. So those are just done the same way as we've been talking about. And colligative properties, where you're given, again, something you have to find the molality of, and then you need to find the final freezing point of the solution. Do the same thing for boiling point, and the same thing for vapor pressure, and the same thing for osmotic pressure. So for the questions 21 and 22, you're looking for molality. You are given the formulas up here. You can see them here. Okay. Let's see.
I have a question.
Yeah. Mm-hmm.
So for one of them, you need the temperature for the osmotic pressure.
Yeah.
When we convert it to Kelvin, do you want us to use 273.15 or just 273?
Well, the thing is that I generally will give it to you with no decimal places, so it won't matter. So if you use 273,
Okay.
it would just be whatever you do, add them together. But if you use 273.15, you'd be rounding the 0.15 back to 0 anyway.
Okay.
So the answer is it wouldn't matter. All right, these are all done with a bit of tolerance as well. So you don't have to get exactly the answer I got, but you need to get close to it. All right, any questions? Any questions? All right, let's take a look. I'm going to get out of here. So I would definitely say, yeah, for these kinds of questions, you don't want to be leaving this to the last day. You know, I think you want to be working on this before the test, is what I'm saying. A lot of people tend to leave studying for the test until the very last day. And honestly, I think it has a negative effect on grades. I mean, the thing is, this should be a breeze for everybody, because you've got, I mean, how often is it that you can actually take a test as many times as you like before actually taking a real test? Figure out what you're doing. But the thing is that people just don't take advantage of that. They end up doing it on the same day, and they might take the practice test maybe twice. If they're lucky, maybe twice. I don't know. I can't figure that one out. I can't figure that one out. I've tried to do some research on the internet, figure out why people don't take advantage of that, but I don't know why people procrastinate and everything else. I don't know. I just can't. I can't get my head around it. I just can't. All right, so just showing you where we're at in the scheme of things here. So today we were looking at all of these concentration calculation type things. This is where we're at, or April 15th right now. On Tuesday, I'm going to be talking about coordination chemistry and DD splitting. And the next Thursday, it'll be review. So it'll be test 4 review. This is, you know, it's kind of sneaking up on us. And then the following Tuesday, the test will be due. So, you know, you've got a lot you can already do. You can do everything on this test up to coordination chemistry. So this weekend, you could actually start working on this and making sure that you understand how to do these calculations. If you don't do it, well, I think it's kind of foolish, really, because you're leaving yourself in quite a bind. The other thing, of course, you need to make some time for is the units quiz, which for this test is a little bit more complicated than it was for the previous test. And you also have to do the essays, test 4 essays as well. So, you know, the work for this is sort of piling up. I don't want people to be sort of left behind, but I can sort of see that happening, because I know that a lot of you are going to leave this till the day it's due, which I think, I'm just going to say, is stupid. Is stupid. I'll say it again. I'm not going to mince any words here. It's stupid. But anyways, that's my opinion. You've got to handle your time the way you've got to handle your time. But I think it's a very bad decision, a very bad choice to leave until the last day.
I have a question.
Mm-hmm.
Is it still a thing that if we get an A average on just the test grades, no extra credit included, we don't have to take that final?
No, it's not an A average. It's the lowest. If the A is the lowest score on the complete test, Alexandra. So after test 4, I look at all your complete test grades. Let me be more specific about this. I'm actually going to go in here as a student to show you. So this is per what I got on the syllabus. So what I look at here, or what the grade book looks at, test 1 complete, test 2 complete, test 3 complete, test 4 complete. So as long as these are all above 90, you can avoid the final and get an A in the class. If any of these are below 90, then you're going to have to take the final to get an A. It doesn't matter about the average. All that matters is the lowest score. And the reason for that is that if you're going to avoid the final, then with an A, then you must have got an A on everything. That's the way I see it. An average can hide a low score. I don't want that to happen. So that's how that works out. Do you understand that?
Yeah, I understand.
Okay. You might not like it, but you understand it. All right. Now, usually students don't like that. They like to be able to do an average. But I figure, if you're given the opportunity to exempt the final, then you really had to have earned it, in my opinion. All right. Anybody got any other questions? Anybody got any other questions? All right. Well, we'll leave it there for today then. And I will see you hopefully on Tuesday. And we'll finish up the stuff with the coordination chemistry.
Hey, Professor,
Yeah.
what if the final's your lowest score?
What if the final is your lowest score? Then it
Yeah.
just gets averaged in with your other test grades.
Okay. So if you take the final, then the grades based on the average of all 5 tests?
It is.
Okay.
But if let's say you had a B already at the end of test 4, it wouldn't matter how badly you did on the final, you'd still have the B. So it won't affect your grade that's calculated at the end of test 4.
Okay. Thank you.
Okay. You have nothing to lose by taking the final, I guess, is the message I'm trying to give you there. All right, any other questions?
So if you have an A in the class by the end of test 4, what grade do you need to get on the final to still get an A?
Well, if you already have an A, it's because you're talking about an average or what here? Because I'm not clear on that question. I mean, if you have an A, then you already have an A, you don't have to take the final.
Well, because like for my example, I've gotten like a high A on all the tests except for my first test I got a B on.
Right.
So my grade in the class is an A.
No, your grade in your class is a B right now. Because it's based on your lowest score, not the average, Alexandra.
Okay.
Yeah. I know it's hard to swallow, isn't it? Because you think it's not fair that you've only got a low score on one. But the thing is, if you're going to avoid the final, then you had to have gotten an A on everything. But what will happen is that, yes, if you've got to be in the class at that point, then you can take the final, and it shows you down here the points needed to get an A, a B, or a C. But this won't really be that relevant until you've taken test 4, and then you'll know your target in order to get an A.
Okay.
All right, that's what you'll do. I know it hurts, but that's the thing. You needed an A on everything in order to avoid the final. I know it hurts, but that's how the syllabus is written.
So, Professor,
Mm-hmm.
so is there going to be like an ungraded copy test of like questions like the final, or we just have to go back from all our tests, test 1 through test 4, and just kind of study those problems?
I think that's what I've done in the, let me see. Yeah, it's not, yeah, I got this final study guide here. And this is what you'll see. So it's question groupings essentially, and you'll notice that throughout all the tests, you've done certain groupings of questions. You can expect the same thing. So the way that you'll study for the final is to go back through those other ungraded copies and be able to do those problems. And I choose 8 of them for the final.
Okay, thank you.
Are you going to tell us which 8 that you pick?
Alexander, I think you already knew the answer to that question before you asked it. No is the answer. I'm not going to tell you. So the other thing with the final is that I'm pretty hard-nosed about this. You'll notice that you have to start it between 8 a.m. and 8:30 a.m. on that Tuesday. You don't get the whole day to do it or to start it or whatever. So everybody does it at the same time. I know it gets worse and worse, doesn't it? All right, does anybody have any other questions? All right, I would recommend
to the essay question and explain that part A and B.
Okay, so this is all here in the notes about the essay question here. What questions do you have specifically, Alexis?
So the A and B aren't related,
No,
right?
they're not.
Okay. So it's a total of 12, right?
No, not necessarily, because you can double up here for part B, and you can do 2 at once. So for example, you could do, if you did this reaction, H2 plus O2 gives H2O, that would actually cover hydrogen and oxygen.
Oh, okay.
So you can double up, find a reaction. You can even triple up if you wanted to, but you'd have to find reactions that involved those elements, and then write 50 words about them. So it could be as few as, well, you might be able to. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You probably do. Maybe you might get away with 5 or possibly 6 of these.
Okay.
Plenty of information about all of these everywhere, though. So if you're smart about it and you kind of look at reactions where you can double up things, then you can actually shorten your workload quite a lot. Any other questions? All right. Okay, we'll leave it there for today, and I will see you all on. Hang on, there is a chat question here. Okay, you already got that. I already answered that one. Okay, thanks. All right. I will see you all on Tuesday.